one more listener in the room. All right. Hello, everyone, and thanks for coming to this week's live seminar, and let me introduce, after a long wait, our colleague from the University of Edinburgh, from over in the city, Ohad Kammar.
Thanks. Thank you for the invitation and the patience. It's a great pleasure to be here, and I guess what some of the benefits of being here so late is that people who wouldn't otherwise be here are here now, which is great. So I'm going to talk about several strands of ongoing work that we started a few years ago, and they're all centered around the concept of a free extension, which I will tell you all about. But it starts with partial evaluation, and that's where I want to start this talk at. And I want to start very, very concretely because one of the exciting things about maths, it's mathematics and computer science, right, all in the same complex. And I want to start in computer science, actually, rather than maths. Okay, for this one. Hope that's okay. So, free extensions. It's a theory, for me, a theory of data structures. So, it's a computational theory for intermediate representations. In computer science, we develop it with intermediate representations, which we use to optimize, compile, simplify, represent proofs and programs. And at the core, what you often need is open terms modulus of notions of semantic equivalence. Okay, so that's kind of a grandiose kind of first slide that one might want to have, but I'm going to show you how it breaks down into very simple things that some of you may have even written. Okay, and it starts very much with partial evaluation, with computation, and motivates algebra. Okay, so Jamie criticized me for not starting with algebra. I will start with computation and build up to algebra. Okay, rightly so. I think he criticized me, but experience tells me the opposite. Okay. Questions are welcome. Okay, so please do interject and shout at me also online. And I'm going to then spend some time on applications, depending on how much time we have. So I want to start very, very, very concretely. Okay. Please.
I actually have a question.
Yes.
Go back.
Yes.
And at the risk of making a seminar last 4 hours instead of 1. How do you make the jump from intermediate representations to open terms? That's a clever sleight of hand to put that in up front. Why open terms?
Why would they be closed? If you have modules, if you have functions, they are all open terms. Yeah. Programs are composed of open terms put together to form closed terms. But if you want to scale things up, you have to understand terms as building blocks. Compilers.
Well, trying to understand why James might ask that.
Yeah.
And I'm guessing, but very simplistically, and I don't believe this myself, I agree with you, but very simplistically, if you have say a lambda abstraction, then you don't need to believe in open terms. You can just lambda abstract everything, and then you're composing closed terms.
You're not doing this type of hands, right? You still have an open term, it's just that people go. Okay. No. But I do want to say with an asterisk, which is a lot of times people replace open terms with lambda abstractions. Okay, so they use lambda that is both a binder and something else. Okay, and what they really need is just a binder. Okay, modulo that, if all you're looking at is the syntax of a lambda term, then that's the same thing. So you are dealing with open terms, even though you close over them with a lambda.
Thank you.
Okay, but really the point is there's some stuff that you don't know yet, right? Because you're dealing with it at compile time, right, or analysis time. Okay, then it's dealing with the unknown that makes it open rather than dealing with variables. Okay, so far so good. Okay. So this is the action box, starting very concrete, right? Because what I'm hoping is that even I think a lot of us have seen action boxes. If you're in academia, you're usually having to deal with an action box. If you're in industry, you usually provide an action box and you charge head and an arm for it, an arm and a leg, sorry. If you're in both, you can kind of manufacture an action box and then convince people to buy an action box because it's somehow good. Okay, so here's the action box. It can do three different things. This is written in Idris, and it runs on my GPU. So it's kind of nice that you can run it on the GPU. So it has a button that you can flick the light on and off. Okay. It has this counter that you can increment. You can press the pink button on the top. You can increment the counter. Okay, that gets a little bit tedious. So you can, turn the dial on the right by some number of degrees, and that also increments the counter. Okay, but that's kind of cheating. So you want to keep track of how many turns you have. So we have a dial that tells you how many turns you have done. Okay, and that changes that only the turns affect the dial. Okay, so this is a very good opportunity for audience participation. Shall I run something on the action box? Any requests? Yes?
Turn 360.
Turn 360. Any other requests? I'm gonna poke Jamie until someone else requests something.
Turn 90.
Turn 90, yeah. Someone else or Jamie next until someone else?
Turn -2.
Turn -2, yep. Great.
Did anything happen there?
Yeah, you can do it again.
Sorry, turn -2.
Yeah, sorry, -2, yeah.
Does it just have complex numbers?
Idris, I will answer that later. I will answer that later.
Turn quotes 2.
No, that's going to crash.
Okay.
Well, no, it's not going to crash. I think it's just going to say what. Okay. No one else is asking the question, I think, so Jamie has to keep on asking. Ink. Okay, very good. So now we can continue. I can show you more later. Okay. So now let's see how the action box gets implemented again in Idris. So I have some state inside. Okay. And in this case, I have the Boolean state of the light, the integer count of the counter, and the integer total number of terms. We saw it will be positive or negative. Okay, and Idris' integers are arbitrary precision. So the computer will crash before the action box will crash. And there's three kind of commands, flick, ink, and turn some number of degrees. And we can apply the commands to the action box. Okay, so there's some states, which is the current state of the light, the current count, and the dial. So far, so good. Okay, so let's go through this. If I flick, I switch the light. On turns to off, off turns to on. If I ink, I add 1 to the counter. And if I turn by I degrees, then I both increment the counter and turn the dial. Okay, and I'm going to point out in this specific case, the actions commute with each other. It's not so obvious that they commute, but I can doing things in each order is the same. That's not essential. It's just a simplifying. It will simplify things later on, but it's not an essential or something. I'm not really making use of it. I'm just making use of it to simplify calculations. Okay, so it's now easy to point that out because you see it. Okay, any questions on this so far? Okay. So that was specific commands. Now we want to start writing programs, right? It gets tedious fast. And I'm going to take a very simple notion of programs. These are just lists of commands. Okay, when I have one of those, so a script is a list of commands, and I can execute the script on the initial state by, for example, folding the apply function from the previous. So that's when functional programming shines. It's just like a one line. Okay, so here's an example: flick, ink, 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 flick on any initial state. I can execute that script, but I need an initial state. Okay, this is where partial evaluation starts. Right? What happens if I don't have an initial state? Okay, so let's write a partial evaluator for scripts. Okay, I have a list of actions. I want to evaluate them without having any script whatsoever. Okay, so I go off my sleeve and I write a partial evaluator. I need to write the kind of the state of the partial evaluator. In this case, I'm aggregating the parity of the number of flicks, okay, in the program, the number of inks in the program, and the sum of the turns. Okay, so this is different than the state I have, which correlates, right, to some degree, the total number of terms with the total count. Here we're keeping them separate. I'm really aggregating the commands I will need to run on my state once I get a state to run. Okay, so I'm making a point of separating these just to clarify the different roles, because we have the small law of the strong law of small numbers. If you don't pay attention, things start to look the same. You don't have too many of them. That's what heights are useful. Okay, they tell us the two things, even though they have the same structure, are actually different. Okay, so these are the abstract commands that we have here. Okay, and any concrete command embeds into the abstract commands. Okay, if I flick, that's just one flick. If I ink, that's one ink, and if I turn by I degrees, that's I turns. Okay, and I have the empty script, right, which is do nothing. Okay, and I can compose scripts by adding things modulo 2, adding the number of increments and summing up the degrees, which might be negative. Right? Okay, so we can execute the script by composing the embeddings of each of them, or you can just write a code that does it. It's not difficult. And if I take this script, I can partially vary it into 0, 3, 0. Okay, and there's no state. Okay, I take this residual script and now I can run it on the given state by, well, I have I flicks left, so I do I apply flick I times, I apply ink J times, and I turn like K degrees. Okay, it kind of writes itself, like always, you get the types right, and everything else just writes itself. Okay, and kind of the perspective that I want to emphasize here is that what we're doing here is algebra. Okay, and that's somehow the forgotten, not really forgotten, but people somehow forget it when they get in the thick of it, the forgotten origin story of algebra. Algebra really is about partial evaluation. Okay, what does the action on a piece of state look like when you don't have a state? What does the action of a linear transformation do to a vector when you don't have the vector? What does the action of a group do when you don't have the thing you're acting on? Okay, that's where it all started. Okay, so what do we have here? We have a cumulative monoid. Okay, so we have commands, times and skip. We have an action of that monoid on our states. Okay, and my point, right? The partially validated actions, in a sense, motivate modern algebra through the Kai's theorem, right? Any action of a monoid on a state is an abstract monoid, and the other way around. Okay, and kind of the point is that partial evaluation is evaluation in an abstract domain, and I'm not gonna. This is not our insight. This is a null idea. Okay, abstract interpretation has taken it to the limit, right, in program analysis. Computational semantics take it to the limit in the context of semantics. So uncomputable things that tell you what's happening at runtime. Okay. The difference for us between abstract interpretation is that there's no over approximation here. We're trying to calculate the terms modulo semantics on the nose. What you can approximate is the semantics you're taking into account. So you can include fewer equations than what you actually have to get a tractable or effective description of the terms modulo equations. Or also in mathematics, it has to be tractable, it has to be effective. Right? If you keep it ineffective, then kind of losing out on the representation. But you want to compute these things. So we want to look at those scripts that are residual. Any questions? Yep.
Well, just I didn't quite catch one thing you said. So, is it important in the algebra that you constructed, the commutative monoid, that you hit the equivalences on the nose? Is it important for this talk that
it is not important for this talk? Sometimes you might not be able to, right?
Yes.
Yeah.
Okay. So you do hit it on the nose in this particular case, but that's not a precedent, it's just a coincidence.
Yes, or in the sense decision. If I really want to, so one of the things you see is that to hit things on the nose sometimes introduces combinatorial complexity, if even sometimes intractability. And then you have a slide to move to say, actually, I'm not capturing the full semantics I have because I want to simplify my computation or my ordinate.
And you're interested in the full gamut of possibilities.
Exactly. On the whole, it's about the theory of all these things together. So being able to slide the knob, right? You have a question, James?
I did.
Yes.
Which is, again, your story goes from a concrete monoid action
Mm-hmm.
to isolating the essence as monoid actions in general without the set on which they act.
Mm-hmm.
So why can't you tell that story just about the apply action?
What is that story that I should tell about the apply action?
I don't know, but I guess there's a monoid of endomorphisms of state, and apply is the action map for that, which is a homomorphism from something to the monoid of endomorphisms. Monoid of sequences of commands.
But you don't always want to include junk in your model, right? So you don't want to look at all possible actions. You just want to look at the ones that come up from your application. Right? So all possible actions is kind of too large, right? It has things that I can't do in my model. I don't always want to include everything.
No, I think we're talking across purposes.
Okay, then we can pick it up offline. Okay. And going slightly more meta, maybe. I want to be able to ask that question. So until I'm in the realm of algebra, I can't even formulate the question, why this and not that. So I want to understand, why does this representation work? What about it that makes it work? Because then I can replace it with other representations of the same thing. And we'll come back to it. Okay. So now, so we talked about open terms. This is so far things were closed beyond the fact that my state was open, the state was unknown. Now let's turn the scripts open. Can write a partially evaluated scripts. Okay, so what's an open script? It's a list of either a concrete command or a placeholder for a big chunk of a script. So instead of each variable of type A, okay, for an unknown subscript, it can come a whole bunch of other commands. Okay, so here's an example where the variables in the script are strings. Okay, and here's an example. It's either split to x 3 times and then split it in. Okay, so these are not just single commands, the subscripts. Full of, there's abstraction here, not just yeah, and these are variables taken from this set or type A. Okay, and like we did before, once you construct the abstract domain for open scripts and open states, things will write themselves. Okay, so I'm going to be writing two kind of abstract domains, O and S, and they're both parameterized by the type of variables for scripts and the type of variables for states. Okay, so it looks like this. So this is what you write in Idris to get that. And because I'm going to be using the fact that these variable sets I'm using have an order, then I could use a more efficient representation than otherwise I would. Okay, so this is what this order constraint is doing. So what's an open command? Okay. Our commands can't mention state variables, so I don't have like a reset to some given state command. So in fact, they not depend on the state variables, the open states. Okay, and an open script has two parts. It has the part of commands from previously. I can partially evaluate all the concrete commands using my closed partial evaluator. And then I have a bag of command variables, and I'm taking advantage of the fact it's a commutative model. It just simplifies it because this representation, but it's not essential. Okay, so an open script, right, has two parts. Move together all the concrete commands, partially evaluate them with a closed partial evaluator, and keep track of the bag of variables that the script mentions. And what's an open state now? Well, it's one of two things. So this is the open script. It has two parts, the static part and the dynamic part. This is called a partially static data structure. And an open state, well, depends on whether you started with a known state or an unknown state. So if you start with a known state, all the concrete commands you have, you can apply them to the known state. Okay? And all the unknown scripts, right, you have to get them on the side in the bag until you know what they are. Okay. Yes.
So there's a certain mental burden here, at least in my mind, to maintain the distinction between commands and states.
Okay.
What I want to do to simplify my life is to pick an initial state and represent a state, an arbitrary state, as a command applied to that state. It's a standard technique. So is there a particular, and you could do that here.
Here you could do that, but that's not general.
Is it not general?
No, we can't always have an initial state in every concrete situation.
So there might be states that cannot be, you can't travel between two states.
Yeah, the whole system might have two different pairs of states and the completely disjoint.
Okay, so that's why you're maintaining this distinction.
Of course, once you add these abstract states, and from the abstract state, once you instantiate, you might end up in one of them. Right? So, but that will not help you with the mental overhead because you already paid the price for the abstract states.
Okay, thank you. Thank you.
Good, I'm loving this. Any more questions? We're only halfway through the data structure. Okay. The second part of the data structure is if I start with a dynamic state, an unknown state, a state variable, and then I have to bag together the whole script that I have. Okay, and that's why I'm reusing my previous implementation. Okay, the first part of the data structure. And part of the point is that this is a combinatorial data structure, going back to the previous question. Okay, and it looks like a mad representation, but there's an explanation of why we chose this to be this way, and that informs everything else. You see, thinking about this as the concrete initial state and an abstract initial state, and thinking of this as the partially evaluated scripts guide the whole implementation in the next slide. And so that's almost part of the points of the theory, that when you have this backdrop of this is why these things work, you can actually come up with more sophisticated implementation and much more combinatorial, much more accurate representations of your open terms modular semantics, because the abstractions help you keep track of what belongs where and where it's coming from. Not sure if I can make that more concrete. Yes.
Two questions.
Yes.
One is a trap.
Okay.
So okay, so bottom of that question, will come back to me. I think I figured out what this reminds me of.
Yes.
Oh yeah, okay. So the trap question was how much of this is original to your work. Don't answer this yet.
Yep.
I figured out what this reminds me of. It reminds me of the ring theory course I did in second year uni,
Yep.
where we extended rings over variables.
Yeah, yeah.
And that's what's going on here.
Yes. You're freely extending a ring with a set of variables. Yeah, there you go. So none of the constructions I think is novel. In fact, I think you have to go quite far to really get the construction, the actual data structure to be novel. I think if you open up a partial evaluator, you'll see these data structures or some approximation of them. Trading them in terms of the theory of free extensions, that's novel.
Novel to your work.
Our work, yeah. Okay. And I'm going to spell out specific work we've done in a few slides when we get there.
Did the people who developed partial evaluators know that they were building free extensions?
As far as I know, they don't. James is going to correct me if he knew differently. I had a successful meeting at the WG 2.11 meeting, which is the program generation, meta programming, partial evaluation working group, telling them about these things, and they seemed interested to hear more. And yeah, so I think there's innovation here, but
Okay.
we're
so
working
the
on it.
three- The bottom line here is what you're saying is just as we say in the title, that the partial evaluation community have rediscovered three extensions.
I don't want to say that because I think that's unfair to the partial evaluation community. I'll return to that. I have a specific slide that I think really touches on that, and I want to have some pictures when I answer that. Yeah, I'll come back to it. Okay, but I do not want to say that's the sentence that you've just said. Okay, you can say it if you want. But I'll come back to it. Any more questions? For good reason as well. I will come back to it. Okay. And now you know again, like I said before, once you have the right data structure, everything just writes itself. And so you can kind of look at it in detail. But if you have a static command, like concrete command, you have an empty bag of variables in it, and you partially evaluate it. You have a dynamic one, like you have no concrete and then just a singleton bag of variables, and so on and so forth. And kind of even the most complicated function here is the action, right, of a partially evaluated script on a partially evaluated state, right? Is you split by cases, either you start with a concrete one, right, or an abstract one, and then you can bring things together and evaluate it. If you really want to, we can spend more time on this slide, but otherwise I'll keep going. Okay, it really just writes itself. And I have another version of this stuff when I write it interactively, but it's not that kind of stuff. Okay. And then you can write the partial evaluator. It feels almost generic. And if you run it on the script I had before, depending on where you start with, this is starting with a concrete state, you can also start with open state, and you will evaluate it to the obvious state. It's very satisfying to actually evaluate it and interesting. And so it's almost generic. So David Kalopemeshingiak and Jeremy Yalop said this should be done generically. And when I saw the talk, I said, oh, there should be universal property here. And in the sense, this is what this is about. Okay, this is kind of this rational deconstruction of what they have done, following others. Okay, so let's try to move to that perspective. I have a monoid action, right? The commands acting on state. And I have this abstract domain, right, for actions. Okay, where I have the command variables and the state variables, and I have these two maps that map either a concrete state or concrete command into the abstract one, or an abstract state or abstract command to the abstract domain. And one thing that I did not dwell on is that this is a homomorphism. I think Jamie would say equivalent, right? Noticing that this is homomorphism, and we're going to be pushing that throughout the story. And knowing it's a homomorphism gives you extra stuff for free. Okay, so now you generalize it. So this slide, I may as well just completely generalize it. You know, saying I have an algebra, a multi-solid algebra. I have another multi-solid algebra that's somehow special, given by some special sets, one for each sort. Okay, with some special homomorphisms and some special index functions. Okay, so here I'm specifically mentioning out the monoid action structure. I may as well talk completely generically about this. And kind of now comes the rational deconstruction is I can do that, so I do that. Okay, I look at multi-solid algebras, an extension of an algebra by an index set, one for each sort, indexed by the sorts, is another algebra B, together with the homomorphism from the original algebra, and index function from the sets of variables. Okay, and point, right, is the representation theorem, which is the representation I've showed you before, is the free extension of the algebra, the actions by the index set of the variables. Yes, Jamie.
So the beautiful example you started off with yielded a commutative monoid.
Action of a commutative monoid, yes.
Where in this picture do properties such as idempotence or commutativity, where on all these arrows and A's and B's would that information be encoded?
So the commutativity comes from the fact that I'm looking at commutative monoids. If I wanted to include idempotency, I would include it as idempotent commutative monoids acting on sets,
So
for example,
where is the?
in the choice of multi-solved algebra. So the theory for those, so it's an algebra, it's a model for some semantic theory. It's in that theory.
So we look at the concrete example, we say, it's commutative, it's
Yeah.
and then we put that information in line 2 and turn the handle on everything else.
You're hitting the nail on the head, right? This is exactly what I want to be able to do. To say, as I'm analyzing my situation, I notice more and more algebraic facts about it, and I want to be able to get more about partially evaluating that stuff in that structure by knowing more about it. The representation might get more sophisticated because I do that, but if I have a library of ready-made abstractions for each theory, then I should be able to get more and more yield for more and more algebraic properties. Okay? Any more questions? Good. Good stuff. Okay, so some consequence of this. So the representation theorem is kind of a fact. Right? The data structure uses a free extension of the algebra of actions by the index set of variables. And now returning it, we're trying to find the algebras, we're trying to find the theorems, we're trying to find representation theorems for the free extension of the algebra by some variables. That's somehow the goal in partial evaluation, or at least from this perspective and this kind of partial evaluation. And I will get to that, I promise, Jenny. Okay, so consequences. So first we have some kind of a spec. Right? If you ever work with universal properties, it feels like you have a spec. Now you have to implement it. And if you have a spec for a wide class of things, you can deal with more complicated situations because the spec kind of says, okay, there's like a checklist of things to check. Okay. In particular, right? So what's the spec? Give me an algebra for some theory. This is representing the abstract of the semantic equalities of interest. I have some set of variables, and I want to represent the free extension of the multi-solved algebra by the index set of variables. Okay, and what it gives you, you can compare partially static data structures in different implementations of the same spec, right, with each other. And there is a trade-off. So, for example, one of the things I assumed earlier was that my sets of variables had an order on them. It's not always the assumption you might be able to make. Okay, you would use different data structures. Yes?
If we could go back one slide, please. What does the word effectively mean?
What do you think it means? So I can represent it in a computer, and it has, and the various properties I need of it are computable. Okay, so the abstract properties realized by computable operations on the data structure.
How bothered would you be, for example, with a factorial explosion in representation space?
I'm going to flip it. If all you have are factorial representations, there's only so much you can do.
Well, because we started off with commutativity.
Yeah.
Commutativity is bad news combinatorial, for example. So even quite simply, I'm not being critical here.
No, I know.
It's true that even in the presence of something simple like commutativity, deciding whether two things are equal.
But you see, in this case, it's actually not combinatorial because
you can put them in a canonical order.
exactly.
Thank you.
Okay.
Yes.
Thanks. Okay, and so you kind of spell out. I have concrete data structure, and you say, okay, which operators do they both support? Which equations do they both validate? And normalize modular, right? Are they sound for these equations? Are they complete? So you get some kind of a theory of why are we using this data structure? We could be using that data structure. If they're equivalent, can we use them in the same situations? So it's kind of an explanatory device, right? But why what we're doing is working? How can we make it work better? Okay, that's what a spec is. You get a theory of it. Okay, so this is the effective point that Jamie brought up. Free extension always exists, but it's not effective. Okay, so will it always exist? The free extension of an algebra by some index set of variables. You take terms over concrete values and abstract values. Okay, and you normalize by the semantic equations and the evaluation equations. Okay, so the evaluation says concrete A, say plus, the plus is any operation in your algebra. Concrete B is concrete of evaluate A plus B in the algebra. So it's a bit more than just the theory. It's a theory together with evaluation of concrete values. So the effective existence doesn't always exist, but in practice sometimes. And that's where you want to win. That's where you want to put your sliding knob. Right? Saying, well, this theory is not effective, but if I give up some equations, I have an effective representation. Another reason for me to have an effective, a sliding knob is to say, well, I'm using this fact, using these equations to get a normal form here. Now I'm looking back at the syntax, and now I'm using a different theory and a different representation to do some other transformation in my intermediate representation. We do it all the time. Okay, that's what compilers, optimizing compilers do. They move in different IRs depending on what they're trying to optimize. Okay, great. So this is the slide now that Jamie wants to see. Okay, he doesn't know he wants to see the slide, but this is the slide he wants to see. Okay, partial evaluators are way more complicated than just this partially static data structure component. Right, they're complicated, big things that deal with a lot of cases. I'm not saying all you're doing all along is universal algebra. No, what I'm saying is if you look at this little cogwheel that is partially static data structure, you can understand it in terms of universal algebra. Okay, when you have this understanding, your fingers itch, and you say, I want to refactor the partially evaluated so that this bit is modular outside. Okay, so we've done that. Okay, you rewrite the partially evaluator so that all it does is communicate with the rest. So the partially static data structure communicates with the rest through the free extension interface. Yes, Jamie.
So if I understand correctly, there's more to this than just universal algebra.
Oh yeah.
Even in the picture you've shown, because in the previous slide, I think if I understand correctly, implicit in this is an idea that there'd be a library of effective representation.
Mm-hmm.
Yeah.
That's the next slide.
Okay.
Okay. So you build it with so that the interface is the free extension, then you write a library of these things. Okay, so if you can slot in a different one, but still have a generic partial evaluator for the rest. Okay. And that's what we've done. So this is some work we've done. We wrote a staging partial evaluator. So you take your term, you partially evaluate it to bring to get the normal form of the term, and then you extract out of it an efficient representation. So this is a very kind of a flattering example. Not all examples are flattering. When you take matrix multiplication in Haskell, it encourages you to write like that. So you say, if I walk relative to any ring, then this is how I do matrix multiplication, and then you can easily just change the ring. Like instead of walking with concrete ring, you walk with an abstract ring. Everything just works. Okay, so this is what we've done. We have some fully concrete matrix that we multiply against a fully abstract matrix. Okay, and we do the multiplication in the free extension. Okay, and you extract out an optimized code. Jamie's smiling. Why are you smiling?
Just enjoying the code.
You're enjoying the code. Okay, great. Yeah, this is with Jeremy Alap and Tamara from Glen. A few years ago now. Okay, and this is a very flattering example because as you ramp up the sparsity of the matrix, right, more things become zero, and then the performance becomes better. So lower is better in this graph. This is Frex, lower is better, it becomes faster. Okay, instead of lightweight out of the box partial evaluation, you just expose more and more algebraic properties in your function, and you pick up one of those partial evaluators in the box, and then make your code run faster, hopefully. Okay. Step 3. So this is just one kind of partial evaluator. You then write more partial evaluators. Okay, so the paper that's not yet that people ask about where it's submitted, that's about equational-proof-synthesis. That's another kind of partial evaluator. And with Sam and Nachi and Nathan, actually should add it. Nathan, don't have a picture. Oh no, here. And Greg Brown, whom I don't have a picture of. We're looking at normalization by evaluation, partial evaluators. then things just kind of slot into place. Yes,
Have three comments.
yes, go on.
I'll just blurt them out. One is a high level point that when you have loads of equations, they can sometimes interact in unpredictable ways. So one place to look for trouble is how individual plausible modules might interact to do inefficient things like go in loops or something.
I have more slides on that. Yeah.
Point number two, one way to try and break this would be to look at practical examples that have compelling equations that aren't quite equations because they depend on some kind of context.
Like call clauses or something, or
Yeah, exactly. So if I were a hostile reviewer, I might say, oh, this is useless because it will never do any practical examples like these. And I just wonder how compelling such an argument might be, what cases you studied. And the third thing that springs to my mind is one of the bottlenecks in AI, in compiler design, is you're manipulating these large complex structures like matrices, and the compiler's bottleneck on piling up essentially partial evaluations, which with a bit of intelligence you could compact down, but the sheer volume of operations and their interactions is too much for the implementers to handle. So my understanding is there's a lot of work in intermediate representations that can do really good partial evaluation. And I just wondered if you looked in that application domain.
Okay, so three questions, three very different answers. Can you just, which I have, can you just find the first question? Sorry.
God, what was it? Anyone remember?
Oh, that's oh, how the equations interact with each other.
Yeah.
Right? So they interact chaotically. That's okay. Okay. So there's no reason why these once you put two equations together, things would interact modularly. So that means when you do have a modular story, that's something you want to celebrate and utilize. Okay, so it's completely right. They do interact with each other in very, very nasty ways. Okay, so it's very hard to say something general about modularity. None of this you can. Okay, that's exciting. Okay,
Something general.
Something combination of general algebras, but for specific theories. Okay, you can also flip it and say, because the combinations are so nasty, you definitely want to have a spectrum of intermediate representations, and you move into one and then out of into another one, out of, and so on, because you're simplifying and transforming different aspects of your program. You really want to have a spectrum rather than just one IR to rule them all. Okay. Second question, right? Now, what was that? That was a Horn clauses. So we did not go down the direction of Horn clauses. We went down the direction of more generalized notions of algebraic theories. So Greg is looking at second order algebraic theories. Nathan is looking at generalized algebraic theories, and we have some initial results there. They're promising. So the story carries over. Horn clauses, the universal algebra is a little bit more nuanced. So I don't know what to say off the cuff. Right? Yes.
You said Horn clauses. I just
yes.
said
Yeah.
context.
Okay. Context. So context, we're definitely thinking about that. Context of binding, context of generalized algebraic theories. Context are quite expressive. So free extensions of a category, for example. Right? Something to calculate, make them look at. Okay. It's kind of very pretty. Third question about linear algebra and machine learning. So one of the projects I just got funded, foundations for type-driven data science. So I'm thinking about those questions and I'm pushing towards that, and things would come together. And this is part of that story as well. So yes, definitely thinking about those areas as well. Does that make sense? Okay. Yeah, my office is currently in the Bay Center, so I think that might give some hint about where my head is sometimes. Okay. Any more questions? I'm actually not going to talk about equational-proof synthesis, okay, but this comes up in the context of dependent types, and I can say a lot about this. Maybe later. So I'm going to skip this. It's about normalization by evaluation. And I want to talk about modularity because this is another thing I can easily communicate now. Okay. Jamie talked about libraries of these Frexlets, like modules that do algebraic simplification. You can start introducing intermediaries in between that take, say, this picture. Sorry about that. That takes some Frexlet, 1, 2, 3, and spews out another one. So the classic example with rings, right? We take two monoids, right? Yeah. Okay, so it's a single structure that combines structures of two monoids that interact with each other. That's quite difficult. We looked at involving algebras and homomorphism graphs. We'll not actually go into all of that in detail, but you can catch me later. Okay, well, the point is that sometimes you can say that. So you have one theory, say monoids, inverted algebras, and it takes any notion of a theory, and you can graph on an involution on it. Okay, you get another notion of algebra. If you have a free extension for simple theory, you get a free extension data structure for the more complex ones. Maybe I'll make it a bit more concrete. So invertive algebras. What's an invertive algebra? So what's involved is monoid. It's a monoid. So I have a carrier, concatenation, unit. And I have another operation, involution. So the quick one is strings, concatenation, the empty string, and reversal is an involution. Why is it an involution? Because it's a reversing homomorphism. Okay, if I take two strings, I concatenate them and reverse that. That's the same thing as reversing the second one and concatenate on the reversal of the first one. The order gets flipped. And reversing the empty, the unit of the monoid is the unit. And doing reversal twice, that's the involution aspect of it with the identity. Okay. Here's another example of invertive algebra, linear transformations or matrices. Touching back on your point. Okay, so a matrix is with dimensions m by k matrices. We're looking at all of them. Matrix multiplication, which is multi-sorted identities, and transposition that flex the indices. A times B transpose is B transpose times A transpose. That's another example of a invertive algebra that is multi-sorted. This is actually quite I think in live I can say that. This is obviously linear algebra. It is great and it's applied, but it's also the theory of categories and composition of categories and identities. So it's exactly the same example. So yeah, you can say categories, you can say linear algebra, and somehow you either applied or very theoretical, which is interesting. Okay. So theorem, right, for invertive algebra, okay, the free extension of an invertive algebra is the free extension of it as an algebra, but with twice as many variables. That's what I mean by modularity. Okay, I've built a free extension data structure for algebras, and I get a free extension data structure for invertive algebras, like a Frex transformer. So Frex is transformer. That's what I mean by modularity. And I don't know if that's what you were touching on when you talked about combining different theories in different ways.
So is this a box that will turn that adds an involution to a flexor to give you a flexor to give you another flexor with an involution?
So your original algebra already had an involution, but if you're looking at it as an algebra without the involution, you can't make sense of the involution. It's just some kind of an opaque operation. Now you can make sense of the involution, get more equations. So that's what I mean by as you study your domain better, you get more out of it as you understand it more. And if you think of, say, equational-proof-synthesis as a way of understanding your model, because what I'm doing is I say, okay, I've proved that what I have is a monoid, and I can use the monoid axioms to prove it's invertive monoid. I'm benefiting. I'm kind of sliding and fitting back, right, into my algebraic ecosystem. Okay, I gain more with every new algebraic property that I discover, okay, including the ability to discover more algebraic properties. Okay, and then we have two other examples that we'll not cover. So actually, we'll go to the end of the talk. Okay, so kind of wrapping up. Start with partial evaluation and try to motivate algebra. I think it's not completely watertight, this motivation, but it's compelling, I think. To the point where, and this is answering Jamie as well, I've tried in the past to start with the algebra and end up with partial evaluation, and that did not go well. I think the metaphor I use is like a saw. You have a saw. If you go one way, that's kind of nice, and you can do that safely, but you don't want to go the other way. It's quite painful. So it's starting with partial evaluation, and then motivating algebra somehow seems to be easier than starting with the algebra and motivating the partial evaluation. And so if you ever want to go and talk to partial evaluator, I suggest this direction rather than the other, or if you manage to do it the other way around, tell me. Quite, on that direction, on that direction done safely. Talk about partially static data structures as free extension. Again, this is not everything in the partial evaluator, just partially static data structure. And I zoom through some applications, and I can tell you some more about them in one-on-ones. And I will stop here and say thank you.
Thank you very much, Ohad. Are there any more questions?
You showed, well, thanks for my talk. You showed Idris code, or you showed an Idris program running at the start. I couldn't understand how it was related to, sorry, was it using Frex, the library?
So that specific example, I wasn't using Frex, the library, because it was using a multi-sorted version of Frex that we have not yet implemented. The currently implemented Idris Frex is single sorted. Okay, but we haven't used implementation of the single sorted story.
So what would be a single sorted?
Monoids, groups, rings. Yeah.
And you need Frex, you need non-sorted Frex to be able to find that program.
That program is essentially multi-sorted in an essential way. Yeah, because it has states and scripts.
So it's still available.
Yeah, GitHub. We have a github.com/Frex project. I think it links to all the other stuff. For the action box. That's not public yet, no. Sorry. It builds on library of one of Edwin's interns. Idris GL or something like that. If I'm not mistaken. More questions online? Wait, I don't see any.
If anyone online has questions, feel free to unmute yourself and ask. And if anyone here has more questions.
Jamie, I think, had a question.
Yeah, I'll unmute myself. So there's two things I'm remembering from this. One is a theory of adding holes to things, free extensions, but there's more to it than that. There's also you care to efficiently represent these whole things that you've built. So at a very high level, how much of the hard work here is building the data structures with holes, and how much of it is efficiently representing them, effectively, I think you called it, and for example, deciding equality in questions like that.
So we have used the non-effective representation as well in an unexpected way. Well, for me, it was unexpected when we did proof synthesis. Okay, so I'm not only constructing effective ones, I'm sometimes constructing the non-effective ones, specifically the syntactic one. Because I want to have a computational story, even when I have a non-effective one, I would study it alongside an effective implementation of the free extension. Okay. So I very much focus on the effective descriptions, almost solely. Okay. The place in which I did not expect to use the non-effective description was for proof synthesis, where you take the terms, you evaluate them in the effective free extension. Now, the non-effective free extension, it's not effective, but it's still, so the quality in that representation is non-effective, but it's still an algebra. So the unique mediate morphism into it exists.
So I'd expect to see a morphism from the non-effective. Let's just spell out what non-effective would look like. It would look like a jumble of symbols.
Yes.
There'd be no optimization. And the effective representation would all be new. It's like my wife after she's organized the room, right? So you put my wife in a room for half an hour, and all of the books will be sorted by color and author name, and the carpet will be straight. It's amazing. It's amazing. You put me in a room for half an hour, and everything's all jumbled up.
Right.
And they're homomorphically, they're equivalent.
Yes.
Right? And there'd be a morphism from the non-effective representation.
But
Well,
also
there's
the
a
other.
trivial morphism from the effective one to the non-effective just by copying the state over.
Well, yes, but if you were keeping track, if you made sure you keep track of also the proof that this is a homomorphism, then what you get is a proof that if you have equality in the effective description, there exists a proof in the non-effective description. And because that proof is constructive, the proof of the existence of a unique homomorphism, what you get out is the equational proof that the two sides of the equation, which on the effective side are both the clean room, and on the non-effective side are two very different terms. That proof ends up being synthesized out for you using the universal property. Okay, and you can then.
Just to help me understand, what should I think of as being the primitive thing here? Is it the non-effective representation which is mapping to the effective one? Or is it the effective one that's injecting into the non-effective one? Or is it a pair of the effective representation and a proof that it represents a non-effective one?
I don't know how to interpret primitive here. I mean, there are all various aspects of this theory,
Well,
and
let's
they're
take a
playing
simple
different roles.
example. Here's a non-effective representation of the number 5, which is 1 + 1 + 1 + 1 + 1. That's the one that my son was using when he was about 5 years old. So I can think of there being a mapping from this non-effective representation down to 5, and 5 is the one true thing. So can I carry that over here, or are things messed up?
So maybe I can write it. So let's just write that down. That's okay. So I should look here rather than there. So I have my 2 + 3 versus 1 + 4. Okay, these are two different descriptions of the same value. Okay, and I have my free extension, the effective description here, right? So they get evaluated in the free extension. The same thing. To the effect, in this case, it's not free, but to they get evaluated to the same effective description, which is 5. Okay. I also have my my non-effective description, right, which is just kind of terms, algebraic terms, modulo the semantic equivalence. Okay, and I have proved that any map from here, that whenever I have for any other algebra, I have a map here preserving that structure. Okay, so that means that the interpretation of these two values, because they have to factor through this unique value, are the same. And because this map is given constructively for any other algebra, it's even for this one. And all the correctness proof that this map is a homomorphism, I get out the fact that, you know, the term 2 + 3 can be proven to be equal to 1 + 4.
Right, tilde.
Tilde, thanks.
So for me, I think you've answered the question I was trying to ask, perhaps not very well, with the orientation of that arrow from 5 to terms over tilde. That's a key point here. And that's an injection, isn't it? So 5 goes into terms over tilde, but you can't go the other way because the terms might have.
No, you can. I mean, given two terms, you can evaluate them. As a,
The closed terms.
not even open. I mean, if this is the free extension,
The
it's an
fact is
open term.
also open.
The fact is open with no variables. I think we should take that offline
Yeah,
because we also.
thank you.
Okay. Any other questions?
I think that explains quite a few of the moving pieces. Is this the equational synthesis that you
Yeah.
did not show?
Yeah.
Okay.
Yeah.
Yeah. So I can see how you blink and you miss it. Yeah.
How
How
yeah,
blink
yeah.
and you miss it, right?
Well, so we try to slow down when we talk about them. Say, watch out, blink, and you miss this. But yeah.
So I'm going to make one remark.
Yep.
It's not meant in a malicious way, but maybe clarifying people in the room and online, which is at no point in the talk did you describe the property that characterizes what a free extension is.
Yep.
Could you please do that?
Sure. There you go. So I have my algebra.
Yep.
And I have my index. So
Yep.
sort index set.
Yep.
Free extension is another algebra. A,
Yep.
which I write like this, together with the homomorphism here, which we call say star, and an index function here, which we call dime.
So that picture was
Yep, that was in the talk.
recurrent.
But the thing is, if you know enough about three things, from this you can reconstruct what it means to be a free extension. I will say it, and I will reconstruct that, right? And if you don't, me telling you that is not going to convey any other insights, right? Which is why I didn't do it. Okay, but I'm going to do it now because you asked. Okay, so such that, so now this was the structure that I need. Let's ask for the property for any other algebra B and any other two maps. This one has to be a homomorphism, and this one has to be an index function X. Okay, there exists a unique homomorphism here, such as this diagram, which is in the category of algebras and their homomorphisms, commutes, and this diagram, which lives in the category of index sets and the index functions, commutes. Okay, and if you know about three things, that tells you nothing that you didn't already know. And if you don't know about them, this tells you nothing because you don't know what to do with it.
In what sense does the unique arrow live in the category of index functions?
And homomorphism of small disordered algebras is an index function that preserves the operations. So that's why I didn't say it. So sorry, you were a little bit malicious, but normally malevolence, malice was intended, right? Neither is intended here, but that's why I didn't mention that.
No, indeed. But now I can answer that implied moral cloud around the question by saying, this is the picture I have never seen in the partial evaluation literature. Because I don't understand that picture in terms of partial evaluation. So starting from partial evaluation and going to algebra would require me already to have that picture in mind with PE. And I don't have that picture because I think that's, again, a relatively recent discovery.
Yes.
That is not straightforward to grasp.
Yes. But if I start with this, I just lose the crowd.
I see.
And I've tried. And I cut my finger on the saw. In offline, I can say more. Okay? Having fun? Okay.
All right, thanks again, and let's continue this over coffee or tea.